Alright everybody, let's continue. So if you have a repeating decimal that has a non-repeating initial sequence, the technique or the method that we're going to use is a little bit more involved than just writing nines underneath the repeating part. So if we have something like 4.5666666666666 that goes on forever, where the 5 does not repeat but the 6 does, we're going to use the following method for representing that as a fraction. So the first thing we're going to do is we're going to set x equal to the decimal. Then we're going to create two equations. We're going to create the first equation by multiplying both sides of the equal sign by a power of 10 so that the repeating part is the only thing to the right of the decimal. Then we're going to create the first, and it should say the second. This should say second. Blah. So that should say second equation. Second. Sorry about that. We're going to create the second equation by multiplying both sides of the equal sign by a power of 10 so that one repetend, or one repeating sequence, is to the left of the decimal point. Then we're going to subtract one equation from the other and solve for x. And then we'll get a fraction. We're going to simplify that fraction to lowest term. So let's look at 4.5666666. So the first thing I'm going to do, remember, is I'm going to let x equal 4.5666666. Okay? So I'm going to let x equal that. Then what I'm going to do is, remember, I'm going to multiply, to create the first equation, I'm going to multiply both sides of the equation by a power of 10 so that the repeating part is the only thing to the right of the decimal. So in this case, notice that, let me get another color here. So in this case, notice that if I take this decimal point and I move it one decimal place, then 45 will be in front of the decimal, and 666666666, only the repeating part, will be to the right. So that's what my first equation should be. So in order to move the decimal point one decimal point over, I'm going to multiply by 10. So I'm going to say that 10x is equal to 4.5 times 6, 4.5666666 times 10 is going to give me 45.6, and it's going to go on forever. Alright, so that's my first equation. My second equation, I need to multiply by a power of 10 so that one repetend is to the left of the decimal. So in this second equation in the whole number part to the left of the decimal, I want one repetend, or one sequence of repeating digits. So the only thing that repeats is 6. So what I need to do is I need to get this decimal point over so that I have 6 in front of the decimal point as well. So if I look at this top equation, I have 4.5666666. So in order to get 6 in front of the decimal as well, I need to go over 2 spaces. So that's multiplying by 100. So I need to say 100x, and 100x will give me 456.666. Right, remember that 6 goes on forever. So actually we probably should be writing ... after this. ... Okay, so now I have two equations. I'm going to subtract one equation from the other. So I'm going to take 100x, and I'm going to subtract from that 10x. And on this other side, I'm going to take 456.666 6, 6, 6. Remember, this goes on forever. 6. And I'm going to subtract from that 45.66666. And remember, these are going on forever, so dot, 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 dot. Now watch what happens when I subtract. This is the neat thing about this. So when I subtract, I have over here, after these two decimals, decimal points, I have 0.6 that goes on forever. But basically what I'm doing is in this top number I have 0.6 that goes on forever, and I'm subtracting 0.6 that goes on forever in the bottom number. So really what happens is these cancel. 0.6666666 minus 0.666666666 is 0. So I'm taking care of the repeating part that way. So 456 minus 45 is going to actually give me 411. And that's going to be equal to 100 minus 10, which will give me 90. So here I have 90x equals 411. So what you're going to do is solve that equation. So I'm going to divide both by 90. And my fraction will be x is equal to 411 over 90. And I can reduce that. Both of those are divisible by 3. So if I divide 411 by 3 and I divide 90 by 3, I'm going to get 137 divided by 30. And if you divide 137 by 30, you will get 4.56666666 that goes on forever. So we have shown that this is indeed rational because we were able to write it as a fraction. All right, let's look at another one. It says show that 0.89494949494 is a rational number by representing it as a fraction. So what I'm going to do is, the first thing I'm going to do is let x equal 0.8949494 and so on. That doesn't look good. So I'm going to change it. Alright, so what I need in my first equation is I need to have just the repeating part after the decimal. Alright, so the repeating part is 94. So if I take, let me get another color here. If I take, let's see if we can see orange. If I take the decimal point and move it over 1, then that will put just the repeating part after the decimal. So I'm going to move the decimal over 1, I'm going to multiply by 10. So 10x is equal to 8.9494 and 94. And it should be dot, dot, dot. I keep forgetting to write my dot, dot, dot. But that's important because this is not a terminating decimal. It's a decimal that repeats. So we need to remember to put our dots. All right. So now I need to write an equation where one of the repetends will be in front of the decimal. So if I go up here to the top one, let's get my color back, sorry. And I say, well, I need for 94 to be in front of the decimal. So that means I'm going to have to move the decimal point 1, 2, 3 spaces, right? So I need to multiply by 1,000. So 1,000x is equal to 894.66666. 0.94, 94, 94, and so on. Okay? Alright, so now I need to subtract my equations. So I'm going to subtract 1000x minus 10x. And one way you can write this is by saying I'm going to say 1000x minus 10x. And when I subtract that, that's going to equal 894.9494. I'm only going to write it 2 times. Dot, dot, dot. Minus 8.94. 94. Dot, dot, dot. So remember that the reason why I do this is because the 9494s are going to cancel out. The 0.949494 is going to cancel out. So these cancel out, and I'm left with 894 minus 8. And 894 minus 8 is 886. So 886. And on this side, I have 1000 minus 10, or 990. So 990x. So I'm going to divide both sides by 990. And when I do that, I'm going to get x by itself is equal to 886. That's just simple solving an equation. Divided by 990. And I can actually reduce this to 443 divided by 495, I think. Alright, I think you get the idea. I'm going to let you try this last one, 8.364646464, and if you have a question about it, you can ask in class. Just quickly, what I want to say is that if a number is not rational, we call it irrational. The set of irrational numbers are all the numbers that cannot be represented as the ratio of 2 integers, so they can't be represented as a fraction. They are the non-repeating, non-terminating decimals. So consider a number like 4.568923 that goes on forever. It never ever repeats the same group of numbers, but it never ever stops either. The ellipsis tells you that the digits continue, but there is no repetend. There's no repeating sequence. So this is a non-repeating, non-terminating decimal. Likewise, consider the decimal 0.1001, 00001, 000, and so on. This number is irrational as well. It has a pattern, but the same sequence of digits do not repeat. Rational numbers are more common than, this should be an N, sorry, I'll go and correct these. Rational numbers are more common than irrational numbers. So when mathematicians discover an irrational number, it usually becomes famous. So numbers like pi and phi, or sometimes people call that phi, those are all irrational numbers. And also the square root of 2 is an irrational number. Square roots, anytime you have a square root, most of the time, not any time, but sometimes, often when you have a square root that's not a perfect square, then you will end up with something that's irrational. And when we consider the rational numbers and irrational numbers together, we have what we call the real numbers, or the real number system. Alright, so we'll talk about divisibility in the next video.